Hello again. It's good to be back with you. And today I want to talk to you about how to calculate velocities from accelerations using Matlab. Well, that's not Matlab. That's my whiteboard. I'm going to do Matlab here in a second. But what I want to do is show you how to do the problem analytically so we know what the right answer looks like. And then we're going to do the same problem using Matlab. So here we go. I've got a body accelerating over the course of 20 seconds. A body is accelerating. What do you mean by a body? Well, a body is just any moving object, okay? It could be a car, it could be a skateboard, it could be a cheetah chasing after a wildebeest, I don't know, whatever it is. But it's some object that's moving, okay? And it's moving in this way, right? This plot shows how it accelerates. From 0 to 10 seconds, the acceleration is 10 meters per second, pretty much a g. Okay, from 10 to 20 seconds, it accelerates at 6 meters per second squared, pretty much 6/10 of a g. Okay, so the way this works, if you do the plot this way, the area in this box right here, I'm going to call area 1, and that one I'm going to call area 2. Well, when you want to go from acceleration to velocity, you integrate, right? If velocity is dx dt, then v dt equals dx, okay? Because I can push this around just like any other variable, and if I want to make those go away, that's what I do. I integrate. So if I want to go from here to here, I got to integrate. Well, integrating is finding areas under a curve. So a1, let me erase this for right now. Okay, so a1, that's base times height, right? So that's 10 seconds times, oops, not 9.81, 10 meters a second squared. Okay, and I'm going to get 100 meters per second. Okay, get out of your way here. Okay, that's the area under that curve. So that means this right here, that height is a1. Okay, so that height is 100 meters per second. Now if I scooch over here, that distance right there is a2. That's the change in velocity as a result of that acceleration from 10 seconds to 20 seconds. Well, a2, we're going to figure out the same way. Actually, let me clean that up. Okay, so that's 10 seconds times 6 meters per second squared, and that's 60 meters per second. Okay, this is not 60 meters per second right here. This is the change in height on this second plot is 60 meters per second. So that's actually 160 right there, and a2 is 60. So it's a2 is the difference between those. So let me, there, got all the numbers in there. So that's what it's supposed to look like. All right, there's the problem written out analytically. In fact, let me get out of your way here so you can see this. There's what it looks like analytically. Now let's do this using Matlab. This segment brought to you by the letter delta. Okay, here we are with Matlab fired up, and I've got it all cleaned out here. There's nothing in the workspace, there's nothing on the command window, there's nothing in the current folder, and you can see my command history over here. The only thing that I did since clearing the command history was clear the screen. So let's do this. There are a couple of different ways to do the plot we need in Matlab, as there are always in Matlab. There's plenty of ways to do everything. So I'm going to show you one of those ways. If you show this to somebody and they say, oh, well, there's another way to do this, well, yeah, they're probably right. There's many ways to do this. This is just one. If you find another one on your own, good for you. You will learn something useful. So what I want to do here is I'm going to make a dt, all right? Okay, this is a time step. All right, so there it is. It exists now. It's in memory, and you can see what its value is. See that size there, 1 by 1? Matlab means matrix laboratory, and what it's trying to do is think of everything in terms of lists and blocks of numbers. So a scalar, you know, right there, is a 1 by 1 matrix. So that's how it thinks about it. All right, I'm going to need a list of times to get started. There it is. Okay, whoops. Let me type that correctly. Time goes from 0 to 10 by steps of dt. Okay, so there it is. You can see it over here. Minimum is 0, max 10. Okay, that makes sense. Let's say T2 goes from 10 steps of dt to 20. Okay, and by the way, that semicolon at the end of every line here, that is there to prevent this list from being printed to the screen. You generally don't want this stuff printed to the screen. But if you want to see what it looks like, let's get rid of that and execute the command without the semicolon. There's your list. Okay, it's over here just like we want it. This is not usually too helpful, so most of the time we'll put the semicolon at the end. And again, CLC clears the command window. It doesn't clear workspace. So you can see I executed CLC again. If you want to pull these commands back up, there they are. You can copy and paste these over here. You can even copy blocks of them and reuse them. That works out fine too. So I need now a list of accelerations for the first time vector, and they all have to be equal to 10. Well, how do you do that? Well, there's a couple of ways. Okay, there's a command called ones. Ones actually makes either a list or a block of ones. Well, I want to go from 1 to 101 because that's how long that vector is. But that vector length may change if I change dt later. So what I'm going to do is make this a little cleaner here. Go to the length of t1, whatever that is. I don't know what it is, but let MATLAB figure it out. So, and I'm going to take that list of ones, I'm going to multiply them all by 10. Okay, so there it is, and you can see it over here. Size 1 by 101, minimum, maximum. And by the way, by 101, why not by 100? Okay, I'm going from 0 to 10 by 0.1. Should there be 100? Well, no, because there's a number at 0. That's the 101st number. Programmers call that fence post error. Okay, there's another way to do this. I'll show you. I can actually assign every element in the A2 vector, that's this list of numbers, as 6 if I want. This will work too. Works just fine. Let me double check and make sure I got the syntax right. Yeah, there it is. So there it is right there. It goes from minimum of 6, maximum of 6, 101. Okay, we got it. So now there's that. Let's make a plot now. Okay, I'll tell you right now, this isn't going to look very good. Okay, MATLAB will let you plot as many curves on one axis as you want. So there's T1A1, there's the first curve. It's a line. Here's the second line right there. Now, what I'll do here is I'll execute that, and I'm going to move this over, and I'm going to pull this plot over here so we can see what's going on. Well, that doesn't look so good. You can't really see any numbers on there. Well, you can just barely see a blue line there, and I think that's a green one down there. So we've got two problems here. One is those lines aren't connected, and the other one is you can't really see them on these axes. So let's do this. Okay, there's an axis command, and I want to define the limits of the x-axis first. So I go 0 to 20, and then let's see, how about if we go from 4 to 12 vertically? Okay, that should work. Yeah, there we go. That's much better. Now they're still not connected. All right, they're still not connected to each other. But why should they be? MATLAB doesn't know that those are supposed to be connected. It just knows those are two different curves. Well, we can do something here. We can say, hold on. Okay, I'm about ready to put something else on this axis. Okay, here it is, plot, and I need an x and a y. So x goes from 10 to 10. All right, so 10, 10. And y goes from 6 to 10. Okay, does that work? Yeah, there you go. All right, now I'm going to say hold off now. So I want to put something else on there. It's going to, if I try to plot something else, it's going to clear out the axis. It's going to clear this out and make a new plot. It won't keep that. All right, so right now that looks pretty good. Let's do this now. Let's make the velocity. Okay, and I'm going to use cumulative trapezoidal rule. CUM trap Z is cumulative trapezoidal rule, and I'm going to integrate A1 with it, and I got to give dt there. I got to give it the step size. Right? If you don't, it assumes the step size is 1. So I got that, and I can, if I want to edit this, I can just hit the up arrow. I hit the up arrow and got my previous command back. I can do that and do that, So I've got both of those. Well, let's plot those now. Okay, and T1, V1, T2, V2. What's that going to look like? Well, that's not what I had in mind. What's going on? Why is this starting at 0? Well, when I integrated right here, what I got was the change in velocity, not the absolute velocity. To make it the absolute velocity, I've got to add that number to it, basically 100. So let's try this. Let's pull that back. Oops, do that. And let's just add the very last number in V1 to it. Let's add that right there. Okay, and there it is. Okay, that looks better. I'm much happier now. So the last thing I want now is I want to make those two plots as sort of a motion diagram like I did on the board. Well, let's do this. There's a command called subplot that lets you put several plots on one figure. This little window here is called a figure. It says figure 1. So if I type 211, it says give me 2 rows of plots, 1 column of plots, and direct me to the first one. There. Okay. Well, let's see. Let's start calling up commands we've used before. There's one. We used that one before. And what I did is I typed in the first few letters and just hit the up arrow and it found it for me. Well, there, again, it looks not what we wanted, so pull up the axis command. There's that. Then we have that plot command we had to use. So there's that. And you see it reset our axis for us. So it does that on subplot, and it doesn't do it when you're doing a regular plot. I don't know why that is, but okay. Because I didn't say hold on. There. There. Let's do this now. I said hold on, more's coming. There it is. Now I got it right. Okay, now let's go to subplot 212. Okay, there it is. And now I want to plot T1 comma V. There it is. It's got that number added to it. There. That looks pretty good. If we want to hit labels, we can say, or add labels. Okay, I can say time in seconds, and it should show up down here since that's the current plot. There it is. I can go back up to, and no, I don't want that. I do want that. There it is again. And of course, there's also a Y label. Okay. Whoops. Oh. There we go. Watching me type is kind of a strain sometimes, I know. Okay, that should, since I hit 211 last, that Y label should show up right there. There it does. See, even got the superscript too, so that's pretty trick. So 212. There that. And last one. Okay, this is velocity, right? Is that right? It is. And there you go. All right, so there you have it. I've shown how to make an acceleration velocity plot on the board using a two-step acceleration, and then we made the exact same thing in Matlab, having Matlab do the integration for us. All right, I hope this helps, and I'll check back with you next time.